All right, we're off and running. This is the first of the daily FRQs. This is question number 1, so it's supposed to take you somewhere between 15 and 20 minutes to complete this one. I have 15 minutes because that's what YouTube allows me without a hassle, and so I'm going to attempt to do this in 15 minutes. So hang on here. We're gonna cruise right through. This is a little precipitate reaction. And then a couple little stoic problems, a little solubility, equilibrium at the end. So read along with me. They give you a little chart of data. They give us question number 1. It says a student is given the task of determining the iodide content of tablets that contain potassium iodide and an inert water-soluble sugar as a filler. So we've got a tablet that has potassium iodide in it and then some other junk that we don't care about. It says the tablet is dissolved, and the reason it talks about that sugar as a filler is because if the whole thing was potassium iodide, we would just take this and turn in how much iodide and we'd be done with this problem. But that doesn't tell us how much iodide we have. We're going to have to figure out how much precipitates formed first. And so the tablet is dissolved in 50 mils of distilled water, excess of 0.2 molar lead nitrate. And we have iodide and chloride, bromides, iodides. We should be looking for silvers, mercuries, or leads. And there's that lead, so that's where our precipitate is going to come from. It says a yellow precipitate forms, which is filtered, washed, and dried. The data from the experiment is shown in the table above. So they give us a little table. The table has a tablet, it has filter paper, and then it talks about the precipitate that's formed drying several times, and it will ask us a question about that here in a second. And so this is the infamous precipitate reaction that everybody sees the first day of, or the first week probably of pre-AP chemistry. So you've seen this one before at least once. This says, for the chemical reaction that occurs when the precipitate forms, write the balanced net ionic equation for the reaction. So we have potassium iodide here that's reacting with lead nitrate. And so 1A part 1, we have to look at potassium iodide and recognize that potassium is always soluble. And so we are dealing with iodide ions from the potassium iodide reacting with lead nitrate. We've got to recognize that nitrate is always soluble, and so we've got this lead 2 nitrate. Nitrate and potassium won't be there because they're spectator ions. That is also an answer to a question here in a little bit. And so we've got this iodide and this lead that are reacting to form a lead iodide precipitate. It doesn't name the precipitate in the problem, but we should be able to figure it out. We stick those two together. Recognize double replacement reactions. The oxidation number does not change. And so if it's lead 2 here, it's also lead 2 here. You do have to balance the equation. It says write a balanced net ionic equation for the reaction. So we have to balance this guy by putting 2 of those iodides on the reactant side. And then that's it. That's part A1. And then part A2 says explain why the reaction is best represented by a net ionic equation. And it is as simple as saying nitrate and potassium ions remain in solution the entire reaction, and then tell them they are spectator ions. That's what I put. Good enough. You're going to get a point for knowing that they're spectator ions. It's really about using that verbiage of the fact that they're spectator ions. That's it. That's part A. Part B says thus, explain the purpose of drying and weighing the filter paper 3 times. Here, once we formed a precipitate, it says we took the mass in the precipitate, we dried it, and then we dried it again, and then we dried it again. And they ask, why did we dry it 3 times? And the answer is, we needed to dry it until that precipitate mass wasn't changing anymore. And so after the 3rd drying, or between the 2nd and 3rd drying, the mass stopped changing. This indicates that the water has all evaporated. So the question is, explain the purpose of drying it. We needed the mass to stop changing. That would tell us that all the water has evaporated, leaving only the precipitate. Precipitate. Close enough. Good. And so that's our answer to B. I always have somebody that argue about that last digit and go, but they're not the same. It's still losing mass. That last digit is not the significant digits. It's the digit you know plus one additional digit, which makes that 9 and that 8 a guess. And so those are the same. Good. And so we're only accurate really to the hundredths place there. And then we're guessing that last sig fig. That's part B. Part C says in the filtrate solution is potassium greater than, less than, or equal to nitrate. And we mentioned this in the question probably. Up here it says, and this is how we know it's a secret, the tablet's dissolved in 50 mils of distilled water in excess of the lead nitrate. Answer their question. It says is potassium greater than, less than, or equal to. So part C, potassium ions are less. Because the lead nitrate was added in excess. That should be our answer. Ooh, there it is. Potassium ions are less because the lead nitrate was added in excess. Good. It says a filtrate solution. It is what you think it is, right? And so it's the solution that we filtered through up here. That solution that came through the filter paper had just the spectator ions left in it. And then we get into little calculations. So part D says calculate the number of moles of precipitate that's produced in the experiment. So we have up here mass of the filter paper plus the precipitate after the third drying. And so what we need to do is figure out what the mass of the precipitate is and then how many moles of precipitate are there. And so the trick here is this. People love plugging this number in as the grams of precipitate. It's not. That's the precipitate and the filter paper. We have to subtract off that 1.462 to find just the grams of the precipitate. So that's what we're doing at the start of part D here. And so at the start of part D, we've got 1.698 grams. That's the precipitate and the filter paper, minus the filter paper, 1.462 grams. And that gives us that the precipitate weighed 0.236 grams. What is that precipitate? That precipitate is the lead iodide, PbI2. It doesn't want to know the grams of the precipitate. It wants to know the moles of the precipitate. So we have to do a quick little T-chart and go grams to moles of lead iodide. Moles is 1, grams off the periodic table. I have a giant one laying next to me on the floor. And those grams of lead iodide total up to be 461 grams. That gives us our answer for part D. Our answer for part D is 5.11 times 10 to the -4th moles of lead iodide. Make sure you put a unit on that guy. So there's our moles of lead iodide. That's part D. That's what they asked for in part D. Part E comes back and asks us, calculate the mass percent of iodide in the original tablet. So we need to figure out how much iodide we have in the precipitate, because that will be the same as the iodide that's in the tablet. Because all of this stuff precipitated out, we put excess lead in there, which means all of that iodide precipitated out. And so if we can figure out how much iodide was here in this, then we can figure out how much iodide was in the original tablet. And so part E, we are going to take and figure out how much of that lead iodide is iodide. And so it's a little mass percent. So the amount of iodide here, at least the proportion iodide, is the mass of iodide. There's 2 of them in PbI2. And so 127, the mass of iodide times 2 gives us 254 divided by the total mass of the lead iodide, which is 461. That's grams of PbI2. And if we take that fraction, we get 0.55% or 55% of it is iodide in that tablet. How much did the tablet weigh? Not of the tablet, of the lead iodide precipitate. So there's our lead iodide precipitate. How much did the lead iodide weigh? There's the precipitate mass. So 55% of it, or 0.55, times the 0.263 grams of PbI2 will tell us that the amount of iodide in the precipitate was 0.129 grams of iodide. If that iodide is how much is in the precipitate, that's also how much iodide was in the tablet at the beginning. They didn't ask for the grams of iodide in the tablet. They asked for the percentage. They asked mass percent. And so for what we'll end up having here is the 0.129 grams of iodide divided by the total mass of the tablet, which was 0.425 grams from the chart up top. And if we divide those and multiply by 100, it will tell us the mass percent of that, which is 30.6% iodide in the original tablet. What's the rest of it? It's a bunch of the filler, right? The sugar filler is the rest of it. Good. Part F says in another trial, this is kind of conceptual. I've got 2 minutes, so we're going to fly through this. In part F, it says another trial student dissolves 55 milliliters of water instead of 50 mils of water. Predict whether the determined mass percent of iodide will be greater than, less than, or equal to. The answer to F is equal to. It's equal because the volume has no effect on the number of moles of iodide. The water's just evaporate off anyway. And so in part F, where it says in another trial the student dissolves a tablet, the excess water doesn't mean anything because it's not changing the moles. Is it changing the concentration? Yes, but it's not changing the moles of iodide. And so we'll have exactly the same mass of iodide in that solution. Good. Part G is your little solution equilibrium. It says a student in another lab wants to determine whether the iodide content of potassium iodide, but he does not have lead nitrate. They do have silver nitrate though, and it gives us a KSP value. And then we get asked the question here, will the substitution of silver nitrate for lead nitrate result in the precipitation of iodide ion from solution? Yes. The answer is yes. They will both precipitate. Silver will also precipitate with iodide. It asks for an explanation. You can say it's about solubility guidelines, that's fine. You also have a KSP here that is extremely tiny, and a tiny KSP will indicate to you that not very much of it dissolves, and so that is going to cause the silver iodide to precipitate. And then part 2 on G. So yes, silver iodide is insoluble based on a very small K value is what I put. And then part G says the student only has access to 1 potassium iodide tablet and a balance that can measure to the nearest 0.01. Will the student be able to determine the mass of AGI produced to 3 significant figures? And the answer is no. If the scale only goes to the hundredths place, we can't have an answer to the thousandths place. That's as obvious an answer as you can get. It's almost too obvious. All right, I'm at 1447, so I'll check back in with you in the next problem tomorrow. Thanks for being great. Take care of yourself. Stay healthy. Bye.